Hello, ladies and gentlemen. Welcome back to day 6 of chapter 1. We are looking at section 1.3, day 2, measuring spread, both range and standard deviation. By the end of this lesson, you will be able to calculate and interpret measures of variability, both range and standard deviation, for a distribution of quantitative data. You'll also be able to explain how outliers and skewness affect measures of variability. Again, when we finish this lesson, these are the practice problems that you should attempt. Let's dive in. So 1.3 day 2, we are still looking at describing quantitative data with numbers. And you can read much of this information on pages 59 to 60. Right? Measuring variability for the range. All right, so what is the range and what does it measure? The definition: the range of a distribution is the distance between the minimum value and the maximum value. We calculate the range as follows. So range is equal to the maximum value in a data set minus the minimum value. You must actually complete the subtraction. All right, so the range of a data set is a single number. It's a calculation, meaning that you must complete the subtraction, not just identify the max and min. All right, if you're describing variability, like how much things vary using the max and the min, you could say the data set varies from this number to this number. But if you are identifying the range calculation, you actually have to complete the calculation to give the range value. Just like it's not enough to show the addition and division for calculating mean, or to show the two numbers in the center of a distribution for median, you would actually have to add them and divide by 2. Same thing for range. You actually have to complete the calculation. All right, so here's an example. All right, below is the dot plot illustrating the distribution of the number of goals scored in 20 games played by the 2016 U.S. women's soccer team that we explored in section 1.2 and that we were also looking at a little bit in the last video. All right, the range of this distribution is 10 minus 1, which equals 9 goals. So the range is 9 goals. This shows your work for calculating that range. But the range of goals scored is 9 goals. So which of the following statements would be correct? So option 1, the data values range from 1 to 10. No. So incorrect. Option 2, the number of goals scored in 20 games played by the 2016 U.S. women's soccer team varies from 1 to 10, a range of 9 goals. So this explains the minimum to maximum variation, but actually calculates the statistic of the range. All right, remember, statistics are calculations that we complete with the sample that we take. So this has a range of 9 goals. Be very, very careful with how you describe this. Wording can be everything in statistics. All right, let's take a look at this next page. So what are 2 problems with range as a measure of variability? Why do we have to look at other measures of variability? Well, the range is not a resistant measure of variability. It is greatly affected by extreme values. And as you can see right here, the range is 9 goals, but most of the goals were actually clustered within a 4-goal spread right here. The range of 9 is including these 2, which we think are outliers. We would have to actually check that, but we think these might be outliers. So this range is not necessarily the best way to describe this. The other issue is that distributions with the same range may have very different variabilities from the center. All right, sometimes we want to know how close people are to the center. When you look at these 2 distributions, one of them is unimodal, roughly symmetric. The other is bimodal, roughly symmetric, but the modes are actually on the outer edges, the minimum and the maximum. Both of these have a range of 4 millimeters. But how varied they are from the center value is very different. These are much more tightly clustered around the center than these are. All right, now this next part you can read from pages 60 to 63. And we're looking at measuring variability with standard deviation. So if range is not always the best thing to use, how do we describe the center? All right, so in the distribution below, how far are the values from the mean on average? So let's just kind of take a look at this from a conceptual standpoint. All right, the mean is about, let's see, it looks like we have the same number of points on either side of 4, spread the same distance from 4 on either side. So we're going to say that the mean is 4. And we're going to calculate what's called the mean absolute deviation. Now, we don't use this nearly as often as you might think because there are certain types of distributions that you will be learning about in the next chapter called normal distributions that are defined with the mean and the standard deviation. But just to get a general idea of how far the values from the mean are on average, we're going to go through this. So you need to take your values minus the mean to figure out how far away they are from the mean. So on this side, we have 1 minus 4, which is -3. This is called mean absolute deviation because we're actually going to take the absolute value. We're looking at the mean as kind of being our central value instead of 0 on the number line being the center. Now we're using the mean as that. And if we want to look at the distance from something, distance is not measured in negative values. Right? So we're going to look at the absolute value of this to turn into more of a distance value. So this is 3 units away. The negative meant that it was on the left, but we don't really care which side it's on, just how far away from the mean it is on average. So we're going to change that to a +3 by taking absolute value. Same thing with our 2 2's. Because there are 2 different data points that we're at 2, we need to calculate each one of those separately. So we have 2 points that are each 2 units to the left of the mean. Now to just look at the distance from the mean, or the amount of the deviation, that would just be +2. And that's why we're using these absolute values. 3 minus 4 gives us -1. Take the absolute value to figure out distance, not just distance and direction. So that gives us 1. If we add all of these up, we have 8. Now on this other side, remember, if we add up all of the deviations without doing something to turn them into distance instead of deviation, then we're looking at these two adding up to 0. Right? Remember at the beginning, actually in the middle of our previous video, we looked at the deviations from the mean should add up to 0. In order to figure out the average difference from the mean, we needed to do something to make those deviations positive so that then we could actually add them up and divide. Right? So we're 1 to the right here. 5 minus 4 gives us 1. 2 to the right for 2 of these points. That's why I have 2 2's. And then 3 to the right gives us 3. 7 minus 4 is 3. Add these up, we have 8. And if I take 8 plus 8, that gives me the total absolute deviations from the mean are 16. Now, if I want to find the mean of the absolute deviations, my sum is 16. To find the mean, divide by how many deviations I was dealing with. I was dealing with 8 different deviations, 4 on one side, 4 on another, for a total of 8 deviations. 16 divided by 8 gives me 2. That's our mean absolute deviation. So that's one way that we can work through this. Not necessarily the most useful method, but it is a valid method. Now, the standard deviation measures the typical distance of the values in the distribution from the mean. It is a more commonly used measure of figuring out how far the values are from the mean on average than the mean absolute deviation was. Right? A larger standard deviation means more variability, while a smaller standard deviation means less variability in the values when compared to the mean. So this is a comparison. How far do our data points typically fall from the mean? Now, how do we calculate standard deviation? We're going to start with from a population and also a term called variance. Now, the standard deviation, which we call sigma sub x, so this is lowercase sigma. Previously, we had used this symbol, which is capital sigma for summation, meaning add it all up. Lowercase sigma is used for standard deviation. So this is sigma sub x, is calculated by finding an average of the squared deviations. It's another way to turn our deviations positive. Then taking the square root, the average of these squared deviations is called variance. Right? So sigma squared sub x. Now, why would we take the square root when we're finding standard deviation? Because we squared the deviations in order to turn them positive. There are 2 ways you can turn things positive. You can either take the absolute value of them, or you can square the entire value, including its sign. Standard deviation uses the squaring method for turning those deviations positive, but then you have squared deviations. And we want to look at the typical deviation from the mean, not the typical squared deviations. So to undo the squaring, take the square root at the very end of the calculation. So let's use the dot plot from earlier and kind of play with the numbers to better understand this concept. All right, we're going to assume that the dot plot represents a population. This is the formula for finding, from a population, finding the variance. All right, sigma squared sub x. You find the sum of all of the deviations. Remember how I wrote the deviations up here previously? So x sub I, meaning each of the individual data points, minus the mean. So x sub I minus the mean, data values minus the mean. And then we would square that answer, including the negative signs, which will turn all of those values positive. Sigma, meaning add them up. And then we would divide by how many we have. When you're dealing with a population, we divide by the total number of data points. If you want to find the standard deviation instead of the variance, then once you calculate this, you just take the square root, right? So it's the square root of all of this. If we apply that to what we had previously, each of these deviations we had as 1 minus 4, 2 minus 4, 2 minus 4, 3 minus 4, and so on. So I have my 1 minus 4 and my 2 minus 4, but instead of taking the absolute value, now I am putting in parentheses and squaring it. So the negative 3 that I get from this is negative 3 quantity squared, meaning negative 3 times negative 3. That's where this 9 came from. The 2 minus 4 is negative 2 quantity squared. Negative 2 times negative 2 is 4. So each of these numbers that were inside of my absolute values previously are being squared, which is how I'm getting 9, 4, 4, 1, 1, 4, 4, 9. I took each one of these and I squared them in order to figure out my squared deviations. When you're writing a formula that could stretch out fairly extensively and you want to shorten your work, you can put a plus with this dot, 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 and then plus. If you show the first two calculations that you would expect to make, plus and then 3 dots means continue in this manner until you reach your last calculation, and then a lot of times we will show the final calculation so that people kind of know where that ends. If you add all these squared deviations up, then we would divide by the total number of data points that we had, which was 8. So 36 divided by 8, these all add up to 36, divided by 8 gives me 4. That is my variance. All right, so remember, the variance is the average of the squared deviation. And you calculate variance before you go through and finish calculating standard deviation. So you find the average of the squared deviations first, the variance. That's what I found here. And then I need to take the square root of that squared average of squared deviations, take the square root of the variance, so square root of 4 gives me 2. I actually ended up with the same exact answer as I did when I found the mean absolute deviation. Now, do we always have population data to work with? Nah, which is going to take us to our next page. So how do we calculate the standard deviation for a sample? Now, this is the formula for standard deviation from a sample. I want you to notice that there's this n minus 1 at the bottom instead of n. All right, why do we divide by n minus 1 when calculating sample standard deviation? So first, how to calculate it. All right, and also for the variance, because sometimes you'll be asked for standard deviation, sometimes variance. If we want to combine data sets or if we want to adjust them based on new information, we need the variance to do that to then get to the standard deviation, just like we find the variance within our square root, and then we take the square root. So please keep in mind both of these terms. We use standard deviation when we're describing our spread, but variance is also an important term to know. All right, so first find the mean of the distribution. We need to know that in order to find how data points deviate from the mean. Then calculate our deviations, the value minus the mean. Notice x sub I is just referring generally to our first data point, second data point, basically all the individual data points being having the mean subtracted from them. All right, so value minus the mean for each value from the mean, and square each of the deviations. Now note the order of the subtraction. The order of subtraction matters. It must be value first, then minus mean, not the other way around. Value is always how we start the subtraction. All right, square each of the deviations, then add all the squared deviations, and then divide by n minus 1, and this is your sample variance. All right, so the variance from our sample. take the square root of your sample variance, and then this is the sample standard deviation, so the standard deviation from our sample data. Now, from our earlier dot plot, if we were to do this, our sample variance, right, s squared sub x, we change from sigma to s. A lot of times when we are switching from population data, from parameters to statistics, right, so from population to sample, we go from Greek letters to the English alphabet. All right, so sigma is the Greek letter S, which is why we're using the English letter S here, and we're using lowercase sigma when we're dealing with population standard deviation with the parameter. We're using lowercase s here when we're dealing with standard deviation from the sample. All right, so s squared sub x is equal to 36 divided by 8 minus 1 this time, and 36 divided by 7 is approximately 5.14. And if we take the square root of that, we get 2.27. Right? So this is how that would work out with this. Now, why this n minus 1? That's always a question. All right, the standard deviation that we are calculating is just an estimate of the true standard deviation, the average distance all the values in the population are from the mean of the population. Since we don't know the mean of the population mu, we can't calculate the deviations from mu. Therefore, we use the mean of the sample, so x bar, instead. Because x bar is the exact balancing point of the data will almost always be closer to x bar on average than they will be to the population mean. All right, the data will almost always be closer to our sample mean on average than they are to our population mean. So the sum of the square deviations from the sample mean from x bar will underestimate the sum of the square deviations from mu fairly consistently. To correct for this, we divide by a slightly smaller number, because if you divide by smaller values, you end up with a larger answer when finding the average, n minus 1 instead of n. This helps to correct for the underestimate that we would be making if we were to stick with the n, because our sample data is almost always closer to our sample mean on average than they are to our population mean. And that would be a problem, so this way we can actually correct for that. Now, how do you interpret the standard deviation? So this is kind of a sentence frame that you can use. The, and then fill in variable name, typically varies by about, give me the number, from the mean. And let's see, so I was looking to see if we had one that would allow us to do this with context. We don't yet. We'll get to one. All right, now, what is the smallest that our standard deviation can be? All right, and sketch a dot plot to show the situation. Now, the smallest that your sample standard deviation can be is 0. All right, that is the smallest value. Standard deviation can never be negative because we are taking great lengths to ensure that our sum is always positive by either taking absolute value for mean absolute deviation or squaring our deviations, which automatically turns each of those deviations positive. This sum at the top should always be positive, and a positive divided by a positive is a positive. So the smallest that s sub x can be is 0, and s sub x is always greater than or equal to 0. Now, if there is absolutely no variability from the mean, if all of the data points are the exact same, so no variability, all the values are the same, then we end up with a standard deviation of 0 because there's literally 0 deviation from the mean on average. Now, is the sample standard deviation a resistant measure of variability? Let's explain what this means. No. All right. The use of the squared deviations makes s sub x even more sensitive than the sample mean to extreme values in the distribution. All right, so in this example, the standard deviation of the number of goals scored in 20 games played by the 2016 U.S. soccer team is 2.58 goals. If we eliminate, all right, these two extremes of 9 and 10, then the standard deviation drops to 1.46 goals. Right? That is a huge change in variability from the center. All right, now, as usual, go ahead and attempt these problems, and I'll see you in class.